Bismillahirrahmanirrahim. Hello everybody. This is a new video on limit sub and limit amp. The first question, evaluate the limit sub of 1 plus 1 over n times minus 1 power n and compare it with the supremum of 1 plus 1 over n minus 1 over n. Second question, let an and bn be two real sequences. Show that the limit sub of an plus bn is less than or equal to the limit sub of an plus the limit sub of bn. Give an example when the inequality is checked. Third question, let x and be a real sequence. Let f be a real function which is continuous and non-decreasing at the same time. Then prove that f of the limit sub of xn is equal to the limit sub of f of xn, and f the limit f of xn is equal to the limit f of xn. How about the case when f is non-increasing? Let us start by the first question. Limit sub, how we can calculate it? We take first, so let us consider an equal to 1 plus 1 over n times minus 1 power n. The sub of a k greater than or equal to n, we will call this by capital A n. So we search the sub of k greater than or equal to n. So we have 1 plus 1 divided by n minus 1 power n. K greater than or equal to n, so it is equal to n, then it is equal to n plus 1, n plus 2, and so on. 1 plus 1 divided by n plus 1 minus 1 power n plus 1. 1 divided by 1 divided 1 plus 1 over n times minus 1 over n plus 2, so n plus 2, and so on. Numerical example. If we take n equal to 1, I am sorry for the bad noise. A1 is equal to the sub of a k greater than or equal to 1. Means sub of, we start from n equal to 1. This means 1 plus 1 divided by 1 times minus 1 power 1. The second, 1 plus 1 divided by 2 minus 1 times 2 power 2. 1 plus 1 divided by 3 minus 1 power 3, and so on. The supremum here is equal to, this is negative, so it cannot be the supremum. This is positive, and here we have 1 plus 1 half. So for this, the supremum is equal to 1 and half. A3. Supremum is equal to a and half, and the infimum is equal to minus 2. The supremum is, we can calculate the infimum using the same thing here, infimum. The infimum will be equal to minus 2. A2 is defined by the supremum of AK, k greater than or equal to 2, which is equal to, we consider the first term because we start from 2, then we have 1 plus 1 divided by 2, minus 1 power 2, 1 plus 1 divided by 3 times minus 1, and so on. They came less positive and negative. So once again, this is equal to 1.5. How about I3? I3 is the supremum, and here the infimum is actually 1.33, minus 1.33. This is the minimum, the infimum. The supremum for I3 is equal to AK, k greater than or equal to 3, means the supremum of, we start from 3. This is the first one, but it is negative. We start from 3, we have 1 plus 1 divided by 3, minus 1 power 3, 1 plus 1 over 4, minus 1 over 4, and so on. And here the supremum is equal to 1.25 and quarter. A4, the same thing. We are back to this example. So we need the limit. The supremum actually is equal to two things. If n is even, so is equal to 1 plus 1 divided by n. If n is even, this will be the first one, the great first positive one. And is equal to 1 plus 1 divided by n plus 1 if n is odd. If n is odd, n plus 1 is even, then the power of minus 1 is even, then this is positive, and in the both cases, when we calculate the limit sup, we mean the limit of an when n goes to plus infinity. This is equal to the limit when n goes to plus infinity of the supremum of ak, k greater than or equal to n, and this is what we call the limit sup of an. This is the limit sup of an. So we can use this symbol or this symbol. In both cases, the limit sup of an is equal to 1 in both cases. How about just the supremum on n? If we take just the supremum of n, it is so easy. How we can do it? supremum, I try to do it. I am trying to do it slowly to let you the chance to understand what I am writing. We conclude that in both cases, the limit sup of an is equal to the limit sup of an, the same symbol, and goes to plus infinity, and goes to plus infinity, and is equal to 1. Let us search the sup of 1 plus 1 divided by n minus 1 power n. The sup is equal to 2 cases. N equal to 1, this is negative and it cannot be the sup. N equal to 2, this will be positive and the sup is equal to 1. So, the sup in this case is equal to 1.5 the sup on n. If we compare between them, we will find that the sup of 1 plus 1 over minus 1 power n is greater than or equal, actually is strictly greater than the limit sup of n, which is equal to 1. Here we have negative and positive terms. For n odd, this is negative, so it cannot be supremum. For n equal to 2, this is positive and the greatest one. For this reason, we take 1 plus 1 over 2, which is equal to 1.5. The second question, let an and bn, let an and bn be two real sequences. Show that the limit sup of an plus bn is less than or equal to the sup of an plus the sup of bn. We have, for all n, we have an is less than or equal the sup of an on n, for all n in n. And bn is less than or equal to the sup of bn on n, for all n natural number. If we add both of them, we get an plus bn is less than or equal sup on n plus sup bn on n. If we take sup on na, we will get sup an plus bn on n is less than or equal to sup of the sup is actually the same sup of an plus sup of bn. If we take the limit, we will get here the limit sup of an plus bn and goes to plus infinity is less than or equal the limit sup of an plus the limit sup of bn, and n goes to plus infinity. We can do it in a more professional way, which means that we have an is less than or equal sub ak, k greater than or equal to n. We can do it in this way. And bn is less than or equal sub of bk, k greater than or equal to n. This is more professional in this case. I can repeat it using this. Then we get an plus bn, which is less than or equal to sub ak, k greater than or equal to n, plus sub bk, k greater than or equal to n. This implies that sub of ak plus bk, k greater than or equal to n, is less than or equal to the sub of this one, which is exactly the same thing, sub ak, k greater than or equal to n, plus the sub of bk, k greater than or equal to n. And if we take the limit here, we will take the same inequality. This implies that the limit sub k greater than or equal to n goes to plus infinity, ak plus bk is less than or equal the limit when n goes to plus infinity, sub k greater than or equal to n of ak plus limit sub k greater than or equal to n goes to plus infinity of bk, which is the question. So we have here a formal method and a professional one, which is this one. Give an example when the this inequality is a strict one. So we will give an example. Let us consider an equal to 1, 2, 1, 2, 1, 2, and so on. And bn equal to, this is the term of the sequence, I mean, yeah. Zero minus 1, it can be, yeah, we can take it, 0 minus 1, 0 minus 1, 0 minus 1, and so on. The limit sub of an is equal to 2. And the limit sub of bn is equal to 0. But the limit sub of let us consider an plus bn. An plus bn is equal to 1, 1, 1, and so on. Then the limit sub of an plus bn is equal to 1. And in this case, 1 is strictly less than 2 plus 0. This is This is an example. We can give another example and more. So we have many examples such that the inequality is strict. Yeah. Here the limit, by the way, the limit sup of an, the limit sup of an is equal to 2. The limit of an is equal to 1. The limit sup of bn is equal to 0, and the limit of bn is equal to minus 1. We can take, for example, Cn equal minus 1, 0, 1, minus 1, 0, 1, and so on. In this case, the limit sup is equal to 1, and the limit f is equal to minus 1. If we take, for example, minus 1, then we take minus 1 power n plus 1 divided by n, for n in n. In this case, the limit sup is equal to 1. Why? Because minus 1 power 2 is equal to 1, divided by 1 is 1. The limit sup is equal to 1. The limit f is equal to 0 and not minus 1. The infimum is equal to minus 1. The infimum is equal to minus 1, but the limit f is equal to 0 and not minus 1, because we have just minus 1, just one element. So this is an infimum but not a limit f. How about the question 3, which is the most difficult? So let xn be a real sequence, let us consider yn equal the supremum of xk, k greater than or equal to n. The limit when n goes to plus infinity, and from here we get the limit of yn when n goes to plus infinity. This is equal to the limit when n goes to plus infinity of the sup of x and k greater than or equal to n, and equal the limit sup of x and when n goes to plus infinity. This is the symbol that we use. From this formula, we get that xk is less than or equal to yn for all k greater than or equal to n, because un is the supremum of xk, k greater than or equal to n. Don't forget that f is non-decreasing. This means that f of xk is less than or equal to f of y index n for all k greater than or equal to n. This implies that the sup of f of xk, k greater than or equal to n, is less than or equal to f of y n. This is first. We need to prove that we have the inverse inequality. We need to prove that we have the inverse of the inequality. yn is sup of xk. This means that we can find a subsequence of xn such that x phi of k converge to y index n while k goes to plus infinity. This is the most important approximately idea for the second inequality. Yn is a sup of xk for k. This means that this is the property of a supremum. This means that we can find a sequence which converge to y index n. Yeah, here you have to be careful and you have to be aware about this idea. This means what? This means that f of un, this is equal to, this is f of un. Actually, I can write it like this. The limit of f of x phi, the subsequences when k goes to plus infinity, this is equal to what? This is equal to f of the limit when k goes to plus infinity of x phi of k. And this is true because f is continuous. This is equal, but f of the limit, f of the limit of x phi of k when k goes to plus infinity, this is equal to f of y index n. Yes, remember this inequality. I will start from here. F of un, which is equal to f, the limit of x phi of k goes to plus infinity. This is less than or equal to the supremum when k is greater than or equal to n of what? Of f of x index k. what do we have? We have f of un less than or equal to the supremum of f of xk, k greater than or equal to n, and the first inequality here, we get this inequality. We get f of yn greater than or equal the supremum of f of xk, k greater than or equal to n. So if we use both of the inequalities, we will get equality. Then we have f of yn equal to the sup k greater than or equal to n f of xk. This is the final equation. Once again, f is continuous. This means that the limit of f of yn, when n goes to plus infinity, the limit is equal to f of the limit of yn, and goes to plus infinity. We are just here because f is continuous once again, and this is equal to the limit. This is equal to we are just here, and we will deal with the second. I am just dealing with the first one. This one is f is continuous. This means that is equal to f of limit y and xn is equal to the sup of xk, k greater than or equal to 1. So the limit and goes to plus infinity, the sup of xk, k greater than or equal to n. This side, and the second side, the limit when n goes to plus infinity, sup of f of xk, k greater than or equal to n. This is exactly what we were supposed to prove. This one. Using the same techniques, just we flip, we inverse the inequalities, we will be able to prove this one. Abracadabra, the same inequalities, the same techniques, we will be able. I will just answer the last one. What can be happen if f is non-increasing, and you are worried about the steps when we use the fact that f is continuous and when we use the fact that f is non-decreasing. So we use the fact that f is continuous, I think, 4 times, and we use the fact that f is non-decreasing 2 times. what can be happen if f is non-increasing? If f is non-increasing, suppose that f is non-increasing. This is equivalent to say that minus f is non-decreasing. F is non-decreasing. And in this case, we are in the first case. We consider minus f as a new function. So we take g equal to minus f. From the first identity, we will get what? We will get the limit g of the limit sup of x n. This is equal to the limit sup of g of xk, both of them, x and 1n goes to plus infinity. We can take it like this, and you understand what I am meaning with g. Let us apply this. We have so minus f of the limit sup of x n. This is equal to minus f. This is equal to the limit sup of what? Of minus f of x n. But the limit sup of minus n of x n, we are supposed to remember at the sup of minus a set. This is equal to minus f of a, and the f of minus a, this is equal to minus sup of a. We will use these well-known properties. In this case, this will be minus limit f of xn. If we cancel, and I'm happy, if we cancel minus with minus, we will get f of the limit sup of xn is equal to the limit f of xn. Using the same technique, we will get f of the limit f of xn equal to the limit sup of f of xn. So they are symmetric in some way. I think this is all for today. Thank you very much. See you next time.